Okay, so we introduced the imaginary number. The pure imaginary numbers are just like basically a number attached to I. Complex numbers kind of expand that a little bit. A complex number is anything of the form A plus B I. So A and B would just be numbers, you know, so for example, you could have like 2 plus 3i. That would be an example of a complex number. Technically, you could have like just a 7i, because in that case, the a would be 0, which means you could also have like just a -5, because in that case, b would be 0. So it can be the whole thing, or either a or b could be 0, so you could have just imaginary or just like a normal real number. So any of those would be technically complex numbers. Just like when you're dealing with variables, these are not like terms, which means they can't be combined any farther than that. So again, this expression is known as a complex number. So we're going to be doing operations. We're going to be adding, subtracting, multiplying, and dividing complex numbers. Okay, so the first thing that we do, and this is kind of a strange piece right here, we're going to be equating two complex numbers together. So the main idea we're going with is that two complex numbers are equal only if their real parts are equal and their imaginary parts are equal. Okay, so this is super important. So their real parts should be equal and their imaginary parts should be equal. Okay, so if we're looking the real parts here, the real part is basically anything that's not attached to an I. So on the left-hand side, it's a 2x. On the right-hand side, it's a -14. So when I say their real parts should be equal, that means you can set up like a little mini equation. So if the two complex numbers are going to be equal to each other, their real parts have to be equal to each other, which means 2x has to be equal to -14 in order for that to work out. So that's a pretty simple equation at that point. We're just dividing both sides to get the x by itself. So if x were equal to -7 and we sub that in here, this would be -14, this would be -14, so our real parts would be equal. So we're halfway there. And then the imaginary parts have to be equal. So the imaginary part is a yi on the left and a -3i on the right. So we already know the i's are equal, so we don't have to include that in our little equation. But we know that the part attached, like the b, in this case would be y equals, and then the number attached to the I over here is a -3. So this actually didn't require any solving. Keep in mind your homework could get a little bit more complicated than that and require us to actually solve some equations. But the idea behind it is the same. In order for the complex numbers to be equal, their real parts have to be equal and their imaginary parts have to be equal. So you're setting up like these little mini equations. Okay, next thing we're doing is we are going to add and subtract complex numbers together. Super, super similar to adding and subtracting variables. You combine like terms. So combine the real parts, combine the imaginary parts. Okay, so our main idea here is just to combine like terms. So we'll do this out nice and slowly, just so we're all clear on what we're doing. So our like terms, we've got the real part. So here the real part is 3, here the real part is 2. Notice you've got addition in the middle. So the real part would be 3 plus 2, which is 5. And then the imaginary parts is this, anything that's got an I involved. And again, notice there is addition in the middle. So the imaginary parts, this is a positive 5i plus, and then we have a -4i. So positive 5, -4i, combine like terms, we end up with just an I. So we combine those up, and that's our new complex number. A lot of this could probably be done in your head, but I just want to make sure you know exactly where all the pieces are coming from. Okay, so next piece, careful with this, we've got subtraction. So we could probably do this without being super detailed like this. So we start with the real part. So the 4 is the real part on the left. Your operation in the middle is subtraction. And then 3 is the real part on the right. Okay, so we're going to combine those. These are like terms right here. And then going back to the left for the imaginary part, negative 6i is your imaginary part here. There's subtraction in the middle, and then minus 7i would be your real part on the right. Okay, so again, these are like terms, so we're going to combine those up. So 4 minus 3, of course, gives us 1, and then we have negative 6i minus negative becomes plus a positive. So negative 6i, positive 7i would just end up being a positive 1i. Okay, so that's addition and subtraction. Pretty straightforward, works the same way that like combining like terms with variables does. With this one, we are going to look at a multiplication example. Okay, so it's kind of in the form of a story problem here. So complex numbers, we do use them in electricity. You may have actually seen this in physics before. And in physics, for whatever reason, they use J rather than the imaginary unit I that we have used in the past. So in an AC circuit, it says voltage V, current C, impedance I. So we've got these three different qualities here. They're related by this formula. So the voltage is equal to the current times the impedance. And so they give us an expression for the current, and they give us an expression for the impedance, and we are going to plug them into this voltage formula. So voltage is equal to the current times the impedance, which in our case the current is represented by 1 plus 4j. So remember, j is just the imaginary. And then the impedance is 3 minus 6j. All right, so the important note that I want us to write for this is for multiplication, we are going to be foiling. That acronym first, outer, inner, last. So it's very, very, very similar to foiling, just like normal, variable quantities. So we're still doing first 1 times 3. So 1 times 3, of course, gives you 3. And then O for outside, 1 times negative 6j. So we get negative 6j. I for inside, 4j times 3 would be 12j. And then last, 4j times negative 6j. The 4 and negative 6 multiplied to negative 24, and then the j times j would give you a j squared. So we got a few things that we have to combine here. Remember I mentioned to you that you never, ever, ever leave a power of I, which means you never leave a power of j. So we know that that piece right there, anytime you see an I squared or j squared is automatically equal to a negative 1. Okay, so we're going to replace that. So we've got 3. We can combine these up in the middle because those are like terms. So negative 6j, positive 12j would give us a positive 6j. And then this, negative 24 times negative 1 would be positive 24. Okay, so I'm just going to combine these up. So 3 and 24, I have 27 plus 6j. All right, so that's gives us our value. So anytime you multiply two complex numbers together, you still get a complex number in return because the I squared or the j squared would end up just being part of the real piece of the complex number. Okay, last thing we're going to look at is like pseudo-division. Doesn't really seem like division, but you'll see what I mean. So we're going to define something first called a complex conjugate. So complex conjugates, say we start with a plus bi. The complex conjugate of that is a minus bi. So all the conjugate is it's taking the exact same binomial and just changing the operation in the middle. Notice both of these a's are still positive. All that has changed here is that this is addition and this is subtraction. So if you start with this, the conjugate of this would be addition. The conjugate of addition is subtraction and vice versa. So our conjugates are actually going to be very, very useful. We are going to be able to use the complex conjugate to simplify the complex numbers, okay? So we've got these two examples right here, and once we get through those, that'll be the end of 4-4. So we're working on this, and we want to simplify that into the form of a complex number. So what we do, and you'll understand why we do this once it's done, we're going to multiply the denominator by its conjugate. And we've got this really awesome property about conjugates that if you multiply them, you always get a real number, and you'll see that kind of work in action. So the denominator is 3 plus 2i, which makes the conjugate 3 minus 2i. And I can't just run around multiplying just the denominator. I have to balance it out by multiplying the numerator too. So if you look at this, top and bottom are the same. I'm technically just multiplying by 1. Okay, so I'm going to do lots of cleanup here. So I have this 5i to distribute, so we're practicing some more multiplication. So 5i times 3 gives me 15i. And then 5i times negative 2i would give me negative 10i squared. Okay, we're going to keep cleaning this up, so don't worry. Now in the denominator, we're going to FOIL. So, first would be 3 times 3, and that is 9. Outside would be 3 times negative 2i, negative 6i. Inside, 2i times 3 would be 6i. And then last, positive 2i, negative 2i would be a negative 4i squared. Okay, so we're going to keep cleaning this up. First thing you should notice is that these will cancel. That's the beauty of multiplying by the complex conjugate, is that the outside-inside terms will always cancel each other out. And that's because the operations are opposite. So let's keep cleaning. Remember, for both of these, every single time that you see an I squared here, remember you replace it with a negative 1. Okay, so we have 15i. Negative 10 times negative 1 is positive 10 over. And then here we have 9. These two pieces canceled. Negative 4 times negative 1 would be positive 4. Okay, so first thing in the numerator, we're used to seeing those in the opposite order, so I'm just going to go ahead and swap them. Addition is commutative, so it's totally fine. And then 9 plus 4 gives me 13 in the denominator. Okay, so last thing, I want it to look like this. I want like just a real part and then an imaginary part. So I'm actually going to split them both up over my denominator. It's like uncombining common denominators. So I'm going to split the 10 over the 13 plus, and then I'm going to split the 15 over the 13 and multiply by I. So now you can see it's perfectly in this form. Real part, imaginary part, separated out. So that would be your final answer for that. Okay, let's practice one more of these. So you see now why we do this. When you multiply by the conjugate, you get rid of all the imaginary numbers and you can eventually clean it up to this form. So if we have 3 plus 5i, we multiply top and bottom by 3 minus 5i, which is the conjugate. So top and bottom, so that way you're just multiplying by a fancy 1. So in the numerator, let's distribute that 2i. So negative 2i times 3 is negative 6i. Negative 2i times negative 5i would be positive 10i squared. And let's FOIL in the denominator. 3 times 3 is 9. 3 times negative 5i is negative 15i. 5i times 3 is 15i. And 5i times negative 5i would be negative 25i squared. Okay, so just like the one before, time to start cleaning up. So every time you see an I squared, you can replace it with a negative 1. We should never ever leave an I squared. So we've got negative 6i, and then positive 10 times negative 1, so minus 10, over. Now notice these guys will cancel. That should always happen when you multiply by the conjugate. And then we have 9. This is negative 25 times negative 1, so plus 25. Okay, so same as up above. I'm used to seeing these two pieces in the opposite order, so I'm going to put the negative 10 first, then minus the 6i, and then my denominator will be a 34. Okay, so I'm going to uncombine like terms, split these up. So I'm going to put the negative 10 over 34, and then I'm going to put negative 6 over 34 multiplied by my I on the outside. Last thing is that these can all reduce because they're all even, so I'm just going to reduce everything by 2. So negative 10 goes to negative 5, 34 reduces to 17, just dividing them both by 2. So 6 reduces to 3, and 34 reduces to 17. Don't forget your imaginary number on the outside, so just like the one above, this form perfectly matches up with this. A would be negative 5/17, B would be negative 3/17. Okay, so that's it.